Hello and welcome again with something interesting and new. Last time I was discussing with you viscosity, types of viscosity, and introduction and different ways to find out viscosity, different parameters I've discussed like relative viscosity, specific viscosity, reduced viscosity, intrinsic viscosity, or you can simply say inherent viscosity. So today I'm here again. I'm Professor Dr. Mchem from Dr.Mchem Institute of Chemistry, University of St. Jamshoro. I'm here again with something interesting again. I want you to know today what is calibration, how you are going to calibrate your viscometer, that is Ostwalds viscometer. Okay, so what is basically calibration is, first of all, you should know every measuring device needs to be calibrated before it is to be used, right? And it simply says that instruments accuracy relies on calibration. It's the method to build or compose the instrument to present a result of the analyte's acceptable range, right? And simply it is you cannot run anything directly on the instrument without calibrating it. You need to calibrate the instrument, right? Just to standardize it, right? And there are many other things which I will add up to this, this lecture today, this share. So simply it is instruments accuracy, which this calibration, it regulates. This is what calibration is all about. And today, what is our instrument? Of course, the Ostwalds viscometer we are talking about. We are talking about Ostwalds viscometer. And then in my last video, lecture, I told you how does it looks like, what is its shape, right? It's U-shaped instrument, and it is it has to be fitted inside some sort of a thermostatic bath, right? And we can use gallon camp thermostatic water bath, which is easily adjustable with its knobs, and I can show you in my presentation its picture which I've drawn, right? Again, my beautiful drawings you are going to encounter. So so this is something interesting that I thought that I must let the new students, they should know how to calibrate their Ostwalds viscometer, right? And it is, based on few steps, number of steps which you are going to encounter, and then your instrument will be ready for the use. You can put your samples inside and you can analyze them. So it's basically a thermostatic water bath that is regulated, that can regulate, the temperature towards, below 0 degrees centigrade and above 0 degrees centigrade. So it is, you have to adjust it with the help of a clamp. The viscometer, you have to fit it down inside the water, that is the viscometric bath, right? And you have to, adjust everything. You have to assemble everything before, starting it. And before starting this procedure, this analysis, you need to calibrate it with the solvent, that is, of course, water, that is distilled water. You need to calibrate it with distilled water. So I will start few slides. I have prepared few slides for you people so that you can understand easily how the process goes on, what is this calibration, and how you are going to accomplish Ostwalds viscometers calibration. So let's share the slides. Okay, so let's see here. There we are. Calibration of Ostwalds viscometer, simply, right? I'm Professor Dr. Mchem. I just introduced myself. I don't think so. I don't need to again introduce myself. So I definitely belong to Dr. Mchem Institute of Chemistry, University of St. Jamshoro. So that was my introduction again. So let's get back to what is calibration. Okay, calibration. It comes from what? To calibrate, right? That is to standardize, another word, another term, to standardize, or to rectify, simply, another third term, or to do an evaluation against a standard, right? Just to do an evaluation against the standard. So now you know what is exactly calibration means, right? Let's get back to the next one. Let's calibrate our Ostwalds Viscometer, right? So Ostwalds Viscometer, as I just mentioned you, it is a U-shaped instrument. It has got bulbs, right? And you have to, with the help of a stopwatch, you are going to, watch the time, right? As it leaves the upper mark, it has got two marks, right? The upper mark and the lower one, and you have to fill your water or whatever solvent you are going to analyze, your analyte, right? You put it inside, and then you are going to see how it flows, and you have to measure that flow time when it starts flowing from the upper mark and it ends up to the lower one, right? And then you are going to do the different calculations. You're going to find out different, things after measuring the flow time of your, because every solvent, it flows with different speed, it has got different viscosity. It's never like that the viscosities are similar. They are almost different, right? The flow is different. When you are flowing water on the floor, it flows with a different speed, you will see different speed of its flow, right? And when you flow honey, you will see its, speed, how it flows, right? And if you simply flow something, you can say syrup or some sort of a medicine, liquid medicine, right? And you flow it, it will be in between. Neither it will flow like, its consistency will be like honey, nor like water, but in between something. So all the liquids, they have different, different speeds from which they can, flow, right? So their flow time is different. Okay, so this is the main function of the viscometer, to measure the flow time, right? Okay, so but we need to calibrate our viscometer before we proceed our to achieve our main goal. So now I've written few points and I've selected it from somewhere. You are not going to get it, so I got it for you people so that you can have it and you can easily apply this method, and you will be successful. That's for sure. I give you full guarantee for that. Okay, the viscometer is washed with potassium dichromate, that is K2Cr2O7, or you can use ethanol, that is ethyl alcohol. Okay, and then of course it will be rinsed finally with the distilled water. You have to do the rinsing afterwards, after washing it properly with potassium dichromate and ethanol. And you have to make a solution of potassium dichromate, right? And then you can fill it and you can wash it easily. Or you can use an ethanol. If you have ethanol, you can use ethyl alcohol. That is also, the best solvent for this purpose. And then you can do the rinsing with distilled water. Okay, and what is rinsing? Of course, you are going to fill up your viscometer, and then you are going to tilt it upside down, and then you are going to let it flow, or let it, and you have to rotate it at right clockwise, and then anti-clockwise you are going to rotate, and then upside down you're going to tilt upside down, and in that sense it's going to be, the distilled water will provide a layer inside the instrument, and we will finally call it that yes, it's now rinsed properly. Okay, this is the proper rinsing. Okay, so now a 15 ml of distilled water is filled in the viscometer. Now you will measure with the help of a measuring cylinder. You're going to measure 15 ml, and then you're going to pour it inside the viscometer, right? And is placed vertically in the thermostatic water bath. Now it has to be vertical, right? Like this, right? Like this, you are going to hang it inside the water bath. It will be hanging inside the water bath, right? And it has to be vertical, and you have to I've written also somewhere in my slides that the position of the capillary is supposed to be monitored, which is inside the viscometer. Thin capillary degrees there. And you have to be very careful when you're positioning the vertical, by vertical positioning of your viscometer. So you need to be very careful for that. So, okay, where we were, 15 ml of distilled water is filled in viscometer and is placed vertically in the thermostatic water bath, right? Okay, initial temperature of bath is fixed at 283 degrees Kelvin, right? So now there are different temperatures at which you are going to, repeat this procedure. First, initially you will fix the temperature at 283 degree Kelvin. Then you will repeat the same process for the other temperatures, that is 293, that is 10. You have to give the 10 degree difference between. Then you will record the flow time at 293, then 303, then 313, and then 323 degree Kelvin with a 10 degree Kelvin interval, right? Okay, yes, so initial temperature of the bath will be fixed at 283 degree Kelvin. Fine, we will do it. Yes, now because it is all automatic, so you can easily adjust with the help of a thermostat. It has got a knob where you can control the temperature, and it has got different power buttons. I will show you the picture in the end how it works, right? I have personally worked on this Gallencamp Viscometric bath, so I know how to operate it. I know very well. At Dr.Mchem Institute of Chemistry, I have used this water bath, this Gallencamp water bath, Viscometric water bath by myself. I used to wash it. It's very heavy. The inside, it has got a water tank inside it, and it's very. You are very scary when you are taking it out because it's very heavy. You need someone's help, and then you can. I used to wash it properly with the cleaning mixtures and everything, and then it was supposed to be dried, and then again we used to put it inside the bath, right? So that it should be clear, it should be clean for the usage. So I have used this Gallencamp Viscometric bath by myself at Dr.Mchem Institute of Chemistry, University of St. Jamshire. I've done a lot of measurements there. I've used it in my MPhils and in my PhDs also. So it's still lying there. If somebody is interested, you can see this instrument there, and you can take my help. I can show you, and I can make you understand how it works, right? Okay, so the viscometer is left to attain the temperature of the bath for about 10 minutes. Yes, now you have fixed the temperature at 283 degree Kelvin. Now you are going to leave it for the period of 10 minutes so that it will have the same temperature as the bath, right? Whose temperature? Viscometer's temperature is left to attain the temperature of the bath for about 10 minutes, right? So their temperatures matches. Okay, and then time is monitored. You have a stopwatch at one side. You have kept it at one side. So now you're going to monitor the temperature with the help of that stopwatch, right? After 10 minutes, the time was noted again. Fine. You will have a notebook, right? And you are going to write it down, everything when you are doing these steps. You're following the steps and you're writing it down. Okay, time is monitored by the stopwatch. After 10 minutes, the time was noted as water starts to flow from the upper mark of the viscometer towards the lower mark. Yes, of course, with the gravitational pull, yes, it will flow down from the upper mark towards the lower mark, and this method will be repeated for thrice, right? At least for thrice. And then you will take the mean of these values. Now, after that, you are going to repeat this same this procedure for the temperatures 293 degree Kelvin to 303 degree Kelvin, 313 degree Kelvin, and 323 degree Kelvin. For the rest of the four temperatures, you are going to repeat this same process. This is how you're going to do it. Okay, and this was something about you can say the filling of the water with this distilled water, and left it for some period, right? Okay, then you will repeat the same process for the other temperatures also. Okay, The flow time was evaluated by taking average of the three values. I just mentioned this. You will take the average of the three values and you will evaluate the flow time, right? The three values you have recorded, right? You will note it down on your notebook. Okay. The method was applied for the temperatures, that is 293, which I just mentioned, to 303, 313, and 323 degree Kelvin. The same method you are going to apply. Now, CRC handbook is used, right? It's a handbook for physical constants of physics and chemistry, basically, and for physical constant also we used to call it. And it has got all the constants inside it. So in this book was used to note down viscosity of water. The viscosity of water is, of course, it's known for above temperatures. So all these above temperatures, you will note down the viscosity of the water from CRC handbook. Okay, fine. Now what will happen? Linearity. Now he's saying linearity. Linearity means a straight line, something linear, was observed while plotting a graph between absolute viscosity eta and product of density rho. Now what will happen, that you are going to plot a graph between absolute viscosity, that is denoted by eta, which is this, right? This is eta. In a yellow, you can see it has got the symbol, and a product of density that is called rho, right? So you are going to plot a graph between them. And after plotting the graph, after putting the values, you will see that if you have a straight line, that means our instrument, our viscometer is calibrated, right? This is the proof of the calibration, that we achieve the calibration point. This linearity, it gives us the, proof, yes, that your instrument is calibrated. Okay. Okay, the beta, the calibration constant of the viscometer, was evaluated from the slope of the line. Yes, of course, if there's a straight line, you can calculate the slope. And beta, that is this calibration constant, beta is the calibration constant, it will be calculated from the slope of that line, right? How you are going to find the slope, I will tell you. I prepared slides for you people so that you can understand. Okay, how you will find out your viscometer is calibrated? Now, this is a very interesting question, that after performing this much, procedures, how you are going to find out that whether your instrument, your viscometer, was calibrated or not. So now here in this slide, you can see absolute viscosity equals to eta, as I just mentioned. So now we have a formula, eta equals to rho beta t. Now, what is rho? Rho is the product of density, right? And density. Now we are talking about density. How you're going to find out the density? With the help of a pacnometer, which I just mentioned. I will explain in my next video how you're going to calculate density, right? It's very easy, and but I will show you how you will do it. Beta is the calibration constant. T is the flow time of the solvent, what you are using, right? Or water, right? Of course, we are using water right now. And eta is the absolute viscosity, I just mentioned, right? Okay, now when they are saying again, when eta equals to rho bt, our instrument is calibrated, right? Now he's again saying a very important, this equation is very important. Just note down this equation. When eta is equals to rho bt, that means this eta, that is absolute viscosity, is equals to rho bt. That is this product of density, calibration constant, and the flow time. T is the flow time, right? So, our instrument is calibrated, which I just mentioned it to you before in my slide, that you will get the confirmation when you have a straight line, right? When you plot a graph, right? So here again, I plotted the graph. I plotted the graph again and again so that you will memorize it easily. Now the graph is plotted between, you can say X and Y axis, you can see, right? And it is between absolute viscosity eta on the Y axis and rho t is on the X axis. And here it's 0 right now. Now you can see a straight line. We got, for example, if we got this straight line, right? So now here I've written also graph between eta and rho t is straight line, and this proves that our viscometer is calibrated. This is how you're going to get it, right? This is how you are going to memorize it, or you're going to, you can put it in your memory how it would be like. It would be like this, that you have a straight line. This confirms that our instrument, that our viscometer is actually calibrated. Okay. Now beta is the calibration constant. Yes, we know it's calculated from the slope of the line. I mentioned it earlier. Yes, that beta will be calculated from the slope of the line. Okay. For example, if plot a graph between eta and rho t. Now again, we'll jump to the same. This is the same graph, but I'm in the next stage of that graph. If you plot a graph between eta, that is absolute viscosity, and rho t, and now you are going to calculate the slope, right? How to calculate slope? I have directed here also with an arrow. Okay, now what you are going to do, that you are going to join, you're going to select any 2 points on this line, right? Any 2 points you will select, and with the help of that, you're going to join it with the x-axis and with the y-axis, and then the next point again you're going to join it with the x-axis and the y-axis, right? And now here on the x-axis you will be having different values, right? Different values will be written here, and here also on absolute viscosity would be mentioned here, right? Different values will be on the y-axis too. So now what will happen, that when you are doing all this, that you join this x and y axis, right? You selected the 2 points, right? That is this and this. Now, how you're going to select, how you're going to calculate slope? You will apply this formula: slope equals to a2 minus a1 and b2 minus b1. Now, what you are going to do, that you are going to minus the value that is written here, that is a2 minus a1 upon that is b2 minus b1, and in this way, with the help of this great equation, you are going to get the slope of your line, and you will you will be very happy that yes, you calculated slope of the line, right? And this is the way how you're going to do it. You can do it manually also. If you have a graph, if you have some points over here and some measurements over here, you can easily do the plus minus and then divide them, and you are going to get the slope of this line, right? Okay, so therefore eta equals to rho bt. In this way, the calibration constant beta can also, okay, now if eta equals to rho bt, which we know that absolute viscosity equals to rho bt, that means our instrument is calibrated. This proves. And the calibration constant, how you're going to calculate calibration constant? When you will divide absolute viscosity over rho t, you're going to get the value of this calibration constant. You have the value of b, right? Beta equals to eta over rho t. Now you have this formula. With the help of this formula, you are going to calculate the beta, that is the calibration constant, right? This is very important. So I have collected all this material for you people, because I thought that maybe this is something the physical chemistry students would be interested in, and the organic chemistry students, they would be interested in doing such type of things that are a little bit apart from the reaction mechanisms and things like that. Because I was good at it, so I took a lot of interest in doing the viscosity of my compounds, and I was really very good in calculating the viscosities and going through all the process, because I performed it when I was doing it during my MPhils and in my PhDs also. So I have done a lot of work on viscosity measurements, and it takes real lengthy time. It takes, and I am thankful to one of my colleagues, Dr. Zora. I would mention her name. She really helped me out, though she was my student, but she helped me out because she belonged to physical chemistry. So she, I will acknowledge her name again. Yes, because that's my habit. I never forget people who helped me, and in my research journey or any place or anywhere, I will always acknowledge their name, whether they are with me anymore or they have left me. Actually, it's people who leave me. I never leave people, right? So fine, no problem, no worries. Life goes on. Okay, life moves on. Okay, we have to move on. Fine. So I'm thankful to Dr. Zora. So she guided me. She helped me a lot in this solving all these viscosity measurements, and I would remain grateful to her. And of course to my husband also, Dr. Akhtar Hussain Mughal. He guided me a lot. I have learned all these calculations with his help. He guided me all these things very nicely because he was very good at it. So Yes, the credit goes to him also. Okay, so now third slide, we'll come to the same. Gallon-Camp Viscometric, I entitled it with a name that is Gallon-Camp Viscometric bath. Whether, well, we'll talk about it. It's on the right side. We'll talk about this slide first. Okay, now in the terms of, again, the same graph, that is, of course, the eta, absolute viscosity, and rho t. You have a straight line, right? You have a 0 over here. This is x-axis and this is y-axis, and you have a straight line. Now you know what is the equation of a straight line. Equation of a straight line is y is equal to mx plus c, where y is the y-axis, x is the x-axis, m is the slope, and c is the intercept. Now what is intercept? Intercept is the point, or you can say it's the point at which the straight line, you can say this straight line, it intercepts y-axis, the place at which it is going to intersect the y-axis. This point is called the intercept, right? This is called the intercept, fine. So now here again, I can show you, select any 2 points on this line and join. This is the same graph, but I did it with the exact, you know, and exact of symbols, right? That is etas. And so again, I'm saying same thing, select any 2 points on this line. If you have a straight line, right, you're going to select any 2 points and join them to the x and y axis, right? Yes, we have joined. So here you have a graph between eta and rho t. So you can simply join it with the first point with the x to the x-axis and to the y-axis. You can name it rho t1, and here eta 1. This is rho t2 and eta 2. This is x and this is y. So slope equals to simply eta 2 minus eta 1 over rho t2 minus rho t1. Now you have the values there. Again, I can tell you that you have the values there. So you are going to just do the simple plus minus and just divide them, and you're going to get your slope. The value of slope will be there. Your slope is going to be there, right? So in this way, you can find the slope, right? And how you're going to find beta, I just mentioned it too. That is the calibration constant. How you're going to find that? How you're going to find absolute viscosity? You have the formula, absolute viscosity equals to beta rho t. So see how many parameters you can calculate easily by simply plotting a very simple graph, right? So this is how you goes on with viscosity. Isn't it interesting? This is very interesting. I just adore this topic, right? Okay, now this is your Gallon-Camp Viscometric bath. This is my beautiful drawing. Thumbs up to Dr. Mchem. Right. So, I mean, this is the great drawing I've done. This is it looks the same. If you just go to, I mean, visit there, if you visit Dr. Mchem's Institute of Chemistry Instrumental Lab, you can see this instrument. It's a very huge instrument. It is a very huge, big instrument, a very heavy one, right? Its color is grayish in color, right? So it has got a window over here. This is a window, glass window is there. And this is a water tank, which I was mentioning it to you just before, that this water tank, I used to take it out with the help of some male, person, and I used to get it washed properly, and I used to wash it with my own hands. I washed it properly, and then again we used to let it dry for a few times, and then again with extreme care I again placed it inside it when it's dry, inside that bath, and then we used it. Always used it. It has got these coils, these electronic coils for the, of course, it's a thermostatic water bath, so it is regulated by electricity. Now here you can see this minute drawing. Oh yeah, it's so beautiful. This is the Viscometer. You see, it's Viscometer. It has got these marks, and you see, just keep that thing in your mind, the level of the water. You just see the level, water level, right? The Viscometer is supposed to be dipped inside. I mean, its bulbs are supposed to be immersed inside this water level, right? You keep that thing in your mind. Now this is your Ostwalds viscometer. Now it is suspended vertically. Now here again you have to see the direction of the vertical, the direction of the capillary tube. It is supposed to be vertical, right? It's not supposed to be a little bit tilt. Tilt is not allowed. You have to make sure that it is vertical and it's straight. It is straight and it's vertical, right? Now you're going to fix this with the help of the clamps. Now these are the clamps, and this is a stand I've drawn, and just like that I used to do it, just like that. It's just the same picture because it was in my mind, because I've done it for so many times that I still remembered it, how I used to clamp the viscometer, because viscometer is full of glass. So we have to be very, I mean, you need to have the rubber clamps, the soft rubber clamps, that they should not break the arm of the viscometer, right? So you have to be very patient when you are simply, I mean, screwing up the you are tightening up these clamps. They are supposed to be rubber, you can say. So and here again it has got a knob. From here one end was, I mean, fixed here, and the other with the help of a clamp, and this way it was suspended inside. And then of course this was the regulator, which I was just mentioning it to you. With the help of this, I used to, I mean, you can easily monitor the temperature, that at what temperature you're going to use. And of course we started from 283 degree Kelvin. And here these are the, I mean, pictures of power buttons, different power buttons I have used, up and down buttons. This is just the same thing. It was so much in my mind that when I saw it on the net, I just simply drew it. I mean, just saw it and I drew it. And it's not beautiful, but it's just accurate. It's just the way it looks. It is just the same. So please go, you can simply see it there, and you can use it, and you can, I mean, you can match it with my drawing. It matches with my drawing very much. So this was something about I mean, Camp Viscometric bath. So I had a great experience of using this instrument, and this was, I mean, a superb instrument. And I used and I mean, measured the flow time of all my synthesized ship bases, and then ship based polymers, then ship based resins, then polymeric resins. And I mean, all the resins, they flow with the different, I mean, they have different viscosities. And then I used to calculate all the viscosities. I mean, all the viscosities, that is relative, specific, inherent, reduced viscosities, and then log of eta versus 1 over t. This is also one of the, I mean, this was quite a tough subject. It was not tough, it was very interesting, but it was something, you can say, lengthy, and it took real time, I mean, in completing this work. So this was something interesting. I hope you have understood all these steps of calibrating your instrument, right? And these were, I mean, the very initial steps. And calibration is always a must whenever you are using any instrument. You are supposed to calibrate it nicely and with full accuracy, so that you can get the results you are looking for, right? If you will not calibrate any of your instruments, definitely you are not going to get the required results, what you are going to and what you are expecting, what you are looking for. So you need to calibrate your instrument. So today, I think I'm quite helpful in explaining it to you. All these things, all these slides were helpful to you, and you will read them properly, and you will go through them and just see how simple it was and how nicely you can do it. With the help of all these only 7 slides, you have learned how to calibrate your viscometer, right? So I mean, it's a great gift which I am presenting it to all my viewers, because I never got it from anyone. I mean, did a lot of hard work in getting this method, right? I pleaded so many people, and then I got this method. So, and that method I applied with some, I mean, variations, and then I was, I mean, successful in getting the great results, which today I am sharing with you. So I thought, yeah, I'm sure now you understood how this calibration it goes on, and how you can calibrate your Ostwald viscometer, and what type of steps you are going to you will encounter, and how you're going to how you rinse your viscometer before, and then how you're going to wash it and then rinse it, and then how you're going to proceed it further with the different steps which I just mentioned it to you, how you're going to fix the time at 283 degree Kelvin, and then 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 you will again repeat the same method for the all the other 3 temperatures. The process of this measurement is a little bit lengthy. It takes time, but yes, but the results you're going to get it in the end are just perfect. You will be, I mean, you will be very excited to see the results which you're going to get in the end. So this was about calibration, and I hope you got all the points. Please go through all the steps. Just write down all these steps easily on the notebook. Just write it down, and then you can compare it with my first lecture of Viscometric series, and then just compare the two, and then see that yes, in this way you can calibrate your viscometer. And wherever density is mentioned, yes, the density could be mentioned with the help of pictometer. It's a small bottle, and it has got a cork and that has got a capillary inside it, and when you dip it inside, the solvent also goes inside that capillary. Its method is very easy. You just weigh the empty bottle, and then you weigh it with the sample. I mean, the process is very simple and very easy. When you I will try to let you know how to calculate the density of your with the help of a pictometer, right? So this was about the viscometric calibrations today, and all about how you are going to simply calibrate your Ostwald viscometer, and then your instrument would be ready for using for your actual samples, right? You will run your actual samples after you have calibrated your instrument, right? Your viscometer with the of course with distilled water, and the density, the viscosity of water for all the temperatures you can easily access them from the CRC handbook. Now, in those days, we used to consult CRC handbook, but now, it's all on net, because net was not that common on those days. So now you can easily find all these values from the internet sources. So hope you like my lecture today, and you will share it with your friends. You will learn a lot. Please keep watching, keep learning from my lectures. These are something very basics, but I have seen few people, making students learn these topics. So I thought that I should share my experience with you people, because I've done a lot of viscometric measurements, and I was, the first one I was one of the first few students who have accomplished this goal of using this instrument. I'm lucky enough that I use this instrument, that is Ostwald viscometer, and I use this beautiful Ostwald viscometer and this gallon cam viscometric bath, and I'm very happy that I accomplished all my goals. Thank you very much. See you next time with something new, something interesting, and of course about viscosity, because we are doing viscosity right now. So I will try to find out something very interesting which will make you again focused, and which will force you to watch my video again. Thank you so much. Please take care of yourself and keep watching, keep learning.